This is the first video of Chapter 4, Isomers. This chapter is going to be about the introduction to stereochemistry. Now, when it comes to isomers in chemistry, especially for organic molecules, there are usually two big categories. One is constitutional isomers. Something you should have learned this from chapter 3. And basically, the molecules are with the same formulas, but the atoms are bound differently in different orders. So they look, if you draw the structure of the isomer, they look completely different. Now, the other type of isomer, which is probably even bigger group in the isomers, are stereoisomers. So these molecules, they have the exact same molecules, they have the same connectivity. They simply have atoms bound in a way, they're pointing at a different orientation in the space. Now, usually this kind of stereoisomers, there are two types of stereoisomers. Stereo meaning, sterically different, but nothing else, everything else are the same. So when it comes to stereoisomers, there are usually two types of stereoisomers, cis-trans and isomers with asymmetric centers. So we're going to look at both of them in this video. Usually cis-trans isomers are usually resulted from restricted rotation, and specifically, restricted rotations are usually because of the multiple bonds, especially double bonds or rings. Now, we have to understand that single bonds or sigma bonds are usually rotate freely. So that's because it's just single bonds. But when you have double bonds, which is composed by a single bond with another pi bonds above and below, which prevent the bonds to be rotating. Otherwise, you have to break the pi bond. So when you have a double bond, when we say double bond, when we say carbon-carbon double bond, when on one of the carbon there's a hydrogen and another substance, and then on the other carbon which also has a hydrogen and another substance, when both substances are on the same side of the double bond, then we say it's a cis isomer. When two substances are on the opposite side of the double bond, then we say it's a trans isomer. Now here we can clearly see that the cis isomer and the trans isomer they have exact same chemical formula, they have the same connectivity, but they are not the same molecules because you cannot rotate the double bond to interconvert between these two molecules. They are actually two different molecules. We can see that they even have different melting point and different other physical properties. This kind of a similar feature can be found in ring structures. So ring structures here replacing double bond, becoming rotation barrier. So when substances on the ring are pointing at the same direction or pointing at the opposite directions, then we say these are different structures, different isomers. So cis isomers and the trans isomers basically inherit the same idea of cis-trans in the double bonds. Cis isomer would have the substance on the ring pointing at the same direction, and trans isomer would have substance pointing at the opposite direction. Here's worth to mention that with this kind of solid wedge line, usually that means this particular substance or group is pointing out of screen towards the viewer. And this kind of dot line, that's usually indicating a group that's pointing toward away from the viewer into the screen. So when you, in the first case, you can see both method groups in this example pointing towards you relative to the ring. And then in the other case, two method group as substance, one is pointing towards you and the other one is pointing away from you. And normally if you both pointing towards you or away from you are relative to the ring structure that shown here in the dashed line. So usually if you have dashed line showing the bond, that's showing the bonds right on the screen. Cis and trans isomers are usually pretty obvious in drawings. So they only exist in the compound can possibly exist in compounds with double bond or ring structures. It will not be the feature for anything with single bonds or even triple bonds. Now here we have to understand that when you have double bonds, we're gonna focus on a little bit double bonds, okay? It's not always gonna be cis or trans. So some of the alkenes, that's how we call it carbon-carbon double bond compound, okay? They can be cis or trans isomers. They can also be neither cis or trans isomers. So for example, this is a group with double bond with 2 hydrogen groups. So you can see there's another substance on this double bond. Now whether the substance on this side of the double bond or on the other side of the double bond, it doesn't make any difference because these 2 hydrogens are the same. So you can simply flip this molecule 180 degrees, you're going to get the exact same compounds. Now when it comes to double bonds, it's worth to mention that double bonds do have slightly different stability when they have different substances. Typically, we would say the more substance on the double bond will make it more stable. But usually, when the double bonds possess exact same type of substance, like this case, this middle one, the one on the right, both double bonds possessing 2 methyl groups. The cis one will be usually less stable than the trans one. Okay. So here's the thing. When it comes to double bond stability, the first thing you're looking at is how many substances on it. The more substances on the double bonds, and when I say the more substances, I mean we're counting the total number of substances that's not hydrogen on these 2 carbons. The more the better. So the more substance makes them more stable. Now when you have equal number of substances, then the trans one will be slightly more stable than the cis one. One of the reasons that if that helps you to memorize is that when anything that's hydrogen on the carbon will be larger than the hydrogen. So between these 2 groups, methyl will be larger than hydrogen. On the other one, the red methyl will be also larger than hydrogen. So when you have 2 larger groups on the same side, usually there will be a slightly more space issue compared to when 2 substances are pointing away from each other. So that's kind of way usually students can memorize this kind of thing better. So here's just some of the names. Okay, when we have double bonds, we call them alkenes. It spells almost like alkane, A-L-K-E-N-E. Compared to without double bond, it will be A-L-K-A-N-E, but this one will be A-L-K-E-N-E. When it comes to double bonds, you can have a double bond on the very end of the chain, so we call it terminal double bond or terminal alkene. You may have double bonds inside of the chain, not on the terminal positions. Then we say it's internal alkenes or internal double bond. Or you can even have a ring structure with a double bond as part of the ring, which is called the cycloalkene. Now alkene is the name of this type of compounds. You can also have double bonds as one of the substances. So for example, when you have one carbon chain with a double bond attached to something, the curved line here is showing you another larger group with the other functional groups. Then we say this carbons with 2 hydrogens on the terminal end of the double bond is called the methylene group. Or you can have a completed carbon-carbon double bond attached to another larger molecule. Again, this curved line showing you this is a larger molecule on the other side. It doesn't really matter what it is. So this look like a ethylene group as a substance is called a vinyl group. And then allyl group will be one more methylene group inserted here in between the vinyl group and the larger molecules. So these are some useful names people usually will be used in the description of the substance, double bond substance as substance. Just give you more examples of the cis-trans to the ring structure. So this is a different view of the same molecules. For example, when in the metal structure you have a cyclohexagon shape are drawn in all in dashed line. That means we're trying to view this cyclohexene ring as a planar structure, and then two solid wedge lines showing you the substance of fluorine and substance of methyl are pointing towards the viewer you out from the screen. Anyway, it's in front of the screen. Or a dot line showing you both substances are behind the screen or pointing away from you. Now, if we can take a side view of this ring, we can see a cis stereoisomer of this molecule would be viewed like this. The cyclohexane ring are being viewed from sideways. So you can see half this ring are pointing towards you, whereas the other half of the ring is kind of away from you. And with two substances pointing either both up, down, or up, anyway, when both substances are on the same side of the ring, then we say this is a cis isomer. Now you can compare it to the other possible isomer, which obviously is the trans one. When you have two substances pointing onto the two different sides of the ring, or everything is relative to this ring. When one is up, the other one is down. Doesn't matter which one is what, which one is down though. As long as one is up, one is down, then we say it's a trans isomer. Or you can draw a 2D view of this molecule by having the cyclohexane ring as the plane geometry on the paper or on the screen, and then you can draw the other two groups. One is pointing down and the other one is pointing up, or similarly one is pointing up, the other one is pointing down. Both these two drawings showing the trans isomer. Now you might want to practice on how to draw the cis or trans isomer for both these compounds. You can see currently the structures of both compounds are drawn in a way that all the bonds are drawn in dashed lines. So it doesn't really specify, for example, on this cyclopentane, the two fluorines, which direction these two fluorines are pointing at, whether they are on the same side of the ring or on the opposite side of the ring. Same thing with the other one. With this cyclobutane, the methyl group, the iodo group and the ethyl group are pointing at the same directions or at the opposite directions, will give you cis or trans isomers. You can pause the video here and then see if you can draw it yourself. Practice to draw how you're going to draw the wedge line or dot line. So with cyclopentane, you can have two substances. Now, when you draw the wedge line, you're trying to show the larger end on the substance and the small end on the carbon that's this bond is extended from. And the other one, same thing. The dot line will be have a little smaller end on the carbon that's extended from to the substance. So this will be showing you two substances on the opposite side. So this is called trans. Now, with no change to the central ring, you can have two substances pointing in the same direction, and this will be cis. Now, usually when it comes to cis transimer, you can always draw them differently to show, even though they show exact same geometry. Similarly, you can draw this. One is up, down, this one is pointing up. These two are exactly the same, and these two are exactly the same on the right. And the other molecule will be similarly. If one is pointing down, the other one is pointing up. But the other group is an ethyl group, so your wedge line only goes to one bound. It doesn't go to the next bound. It doesn't draw it that way. You draw the extended bound just like a normal bound, which is already showing you this bond is pointing up, away from out of the screen, and the other line is pointing into the screen. This is iodide. So this will be two substances on the opposite side of the ring is going to be trans. And then when you have both substances on the same side, doesn't matter up or down, as long as they're on the same side, then this is cis. Now that's one of the type of isomer. The other type of isomer is the isomer that contain asymmetric center. So first of all, what is the asymmetric center? This is mainly referring to an sp3 carbon. Again, asymmetric center is usually okay, referring to sp3 carbon. Now we have to understand one of the keywords in this type of isomers, which is called chiral. And the opposite of that is called achiral. Now, any chiral object basically have a non-superimposable mirror image. Typical example will be your left hand and your right hand. And a chiral object, obviously, that's going to be opposite of the chiral center. It has a mirror image, but that mirror image is superimposable with itself, such as a symmetric. Any symmetrical object will be superimposable with its mirror image. Now, how do this apply to chemistry? Now, when it comes to chemistry, especially sp3 hybridized carbon, which possess a tetrahedral geometry with 4 bonds pointing away from each other with a bond angle about 109.5 degrees. So when we have a carbon in the center, or any atoms, but most of the time it's going to be carbon, with 4 substances on it, as long as these 4 substances are completely different, then this is a carbon going to be a chiral center, or so-called asymmetric center. Now, sometimes it's pretty easy to see in any molecules with the molecular joints to tell whether a carbon is a chiral center or not. For example, in 2-butanol, this is a chiral center. You can see usually, even though in all of the carbons there's no hydrogen showing, but on this carbon you can see the substance. When we say substance, everything else other than this carbon, including on this carbon, there's 1 substance, 2 substance, and 3 substance. And then the other substance that's not shown is hydrogen, which is obviously different from everything else. Now, in next structure on this carbon, again, there's hydrogen that's not shown. Now, let's look at the substance on this carbon: ethyl, isopropyl, bromo, and hydrogen. And down here on this carbon, there's a hydrogen here. Every carbon needs to have 4 bonds, right? So 1, 2, 3, 4. Ethyl, methyl, isopropyl, and hydrogen. Now, sometimes people might be confused for some of the carbons. For example, this carbon has a hydrogen. Okay, so it has 1 substance, 2, 3, and 4. Everything else will be the 4 substances. On this carbon, though, there are 2 methyl groups which are exactly the same. So there's no way this carbon can be a chiral center. Now, normally when you see primary or secondary carbons, they're not chiral centers. For example, now this carbon has 2 hydrogens on it, which are exactly the same. So this carbon is not a chiral center. Now, when you have carbon with 4 different substances, the mirror image will be non-superimposable as the original structure. So when we have a molecule which has a non-superimposable mirror image, then we say these 2 molecules, one is the original one, the other one is the mirror image of it, they are enantiomers. So enantiomer is a relationship. When 2 things are non-superimposable as mirror images at the same time, then we say these 2 compounds are enantiomers. They are also a type of stereoisomers. Enantiomer obviously is caused by this chiral center. So when you have a carbon with 4 different substances, then this carbon is a chiral center. When you have one chiral center, this molecule is a chiral compound. Now, chiral compound must has itself and its enantiomer. Now, here's a very confusing concept. Sometimes students might have a question with. A chiral center and a chiral compound are two different concepts. Chiral center is also asymmetric center, which is any atom with 4 different substances is a chiral center. Now, the other thing is a chiral compound. That means the entire compound. That's a chiral compound, that's a chiral compound. Now, the chiral compound and its mirror image, they both are enantiomers. So enantiomer are like what they call it, what their relationship is, basically. So here's an example, okay, not only showing you what example of chiral center and chiral compounds is, but also showing you how do you usually draw a chiral compound on the paper. So typically when you have a chiral compound and a chiral center, you won't draw this chiral center in the middle, and you won't draw 4 bonds in a way, 2 bonds as dashed line and 2 bonds as the wedge line and dot line. Now here's the thing. 2 dashed lines means the bonds on the screen plane, and the wedge line means the bonds pointing towards you above the screen plane, and dot line points away behind the screen line, all from this chiral center. Now normally when we draw the chiral center, we would draw the carbon, or even you don't have to draw the carbon, just a dot. You won't draw the dash bonds, which are on the plane right next to each other, and then 2 other bonds kind of closer to each other. Normally we would not draw chiral center like that, kind of separate the dash bonds vertically or horizontally. We probably wouldn't draw this with angle either. Okay, just keep that in mind. Normally, I'm just saying normally we would not draw bonds like that. We draw one chiral center. One chiral center will be always drawn like that. So when you have a compound with a chiral center, then you would know it is a chiral compound, and it must have a enantiomer, which is going to be its mirror image. The mirror image can be drawn like this with a carbon, and then everything basically is symmetric to each other from this mirror plane. The other way of drawing a mirror image, if you can't see this kind of symmetry, is to actually, I'm going to use that as an example. When you are given one of the specific isomer or enantiomer of a pair, like what's shown in the example here, the enantiomer of this compound can be drawn almost exactly the same, but you can swap any 2 bonds without changing the substituents on it. You're going to get the enantiomer of the original compound. For example, in this case, you can keep everything where they are now. You just need to swap the wedge line and wedge bond and dot bond. You can draw better than that. The methyl group that used to be down here, I'm going to move up here, and the hydrogen move down here. Now these two must be enantiomer between each other. Now similarly, you can draw the isomer swapping any two bonds, not just these two. So for example, the same enantiomer can be drawn by swapping the ethyl group and Br. So I'm swapping these two groups on the same bond. It will result into the same enantiomer. When I say the same enantiomer, I'm saying compound 1 and compound 2 are exactly the same. We can even swap any two bonds you want. For example, from the original structure, I can swap Br with hydrogen, and then you will get a compound 3. And the 1, 2, 3 are exactly the same. They all are the enantiomer of the first compound, A. These 1, 2, 3 are not 3 compounds, they're actually 1 compound. They're exactly the same. So in next video, we're going to learn how to assign the relative priority to the full groups and assign the chirality of the compound.